My name is Nicholas Bisio, and this is my data science project. Over the next 10 minutes, I'm going to be discussing the median home value analysis I performed in Chicago neighborhoods. So the overall goal of this project, other than exploring the median home value of the neighborhoods in Chicago, was to follow the CRISP-DM pipeline. And just for a basic refresher here, is kind of the pipeline in total. Starting with business understanding, moving along to data understanding, preparation, modeling, evaluation, deployment, centralized around one big database. And if you'll notice on the top left-hand corner of the presentation, there will be a little reminder of where we are in this pipeline as we go through. So this screen here is the project pipeline, and as you can see from the top to bottom, it shows the data collection represented by the blue ovals, and down to the model building represented by the final red rectangle. And so to start, data was collected from two different sources, and let's start on the right-hand side with the Kaggle oval. And at the top there, data was collected from Kaggle in a CSV file, and it represented crime data in Chicago. Now, that CSV file had approximately 10 million records, which is way too many records for what I actually needed for my analysis. So what I did was I uploaded that CSV file into its own database called the crime database in the table crime Chicago. From that table, data was random sampled from there in groups of 20,000 for each year that we were interested in. And that data was placed into an R notebook. Now, in that R notebook, after the random sample occurred, some feature engineering happened, and that was done by using a reverse geocoding API. The data was then cleaned, prepared, and then it was uploaded into the data analytics database using the crime data table. Now, on the left-hand side, the factfinder.com oval, that's a census website, and from that website, data was web scraped. Most specifically, economic data and housing data was web scraped from there, and that was placed into an R notebook. And after the web scraping was conducted, that data was cleaned, prepared, written to a CSV file, and then that CSV file was uploaded into the data analytics database using the tables economics data and housing data. Finally, that data was queried out of that database and brought into the data exploration, analysis, and modeling R notebook, where the multiple linear regression, KNN, and SVM models were created. And that's the R notebook that I'll actually be able to explore with you and run. The other R notebooks I'm just going to explain in the PowerPoint. So now on to the business understanding. The project objective here basically is to predict Chicago median home values. And the data was on a zip code level from 2011 to 2016. And I decided that the attributes I was going to use to make these predictions were going to be neighborhood characteristics, as you saw in the previous slide, housing, economic, and crime characteristics, and because the dependent variable is continuous, I'm going to need to do predictive regression models. And as you saw from the last slide, that turned out to be a multiple linear regression, KNN, and SVM. Now on to data understanding. And so in the data understanding phase, data collection was basically done, and the understanding of the attributes. So the biggest problem was where to collect the data, and I chose to collect the housing and economic data, again, from factfinder.com, and that was web scraping, and the crime data from a CSV file in Kaggle. And now the discussion of which attributes to use was quite interesting. From FactFinder, I used all sorts of different attributes. Some attributes I thought would have better correlation to median home values than others, such as like the median income in that zip code would be pretty highly correlated to the median home value, but things like time travel to work, I wasn't entirely sure if that would be pretty useful. So I kind of used a little bit of everything just to see what would work and what wouldn't. But most importantly, the attributes that were really not that useful for me were all the attributes included in the crime data from Kaggle. So I previously mentioned this before, but in the R notebook that dealt with the crime data, I used a reverse geocoding API. And the reason for that was so that I could calculate I could get the zip codes for each one of the crime instances in that data. And my reason for doing that was that I really was interested in how much crime was occurring in each zip code. So after using the API to create the zip codes, I then created my own feature, which was percentage of crime per zip code. And basically all that involved was adding up or counting all the different zip codes that I had just found out, and then dividing the totals by 20,000 each so that I can get 20,000 being the size of the random sample, so that I could get the percentage of crime that was occurring in each zip code per each year. And that was the attribute that I was really interested in. So that would be considered the feature engineering that I used there. So now on to data preparation. So now data preparation was kind of an interesting part of the project. It definitely took the longest amount of time. And in the two files that I'm not going to be exploring with you here, I performed text parsing and imputation. And that basically, like I mentioned before, involved removing percentage signs from percentages, so that I can transform those into numbers, and commas from larger numbers, so that I can transform those from strings to numbers. So that's kind of the text parsing. And imputation, some of the values for certain years were missing. But as a result, because I was using zip code data over a range of different years, I was able to impute those missing values with the average of that zip code for that given year. And so that kind of solved that problem. But then in the R notebook that I will be showing you, I'll go in less detail here right now, but I will be showing you the data exploration, specifically exploratory plots, outliers, and correlation analysis, as well as data preparation, standardization, and PCA specifically, and I'll show you what that looks like in a minute. But just to round out the rest of the process here before we go into our notebooks is the modeling stage. So specifically multiple linear regression using backward elimination, KNN tuned with a K through 1 through 10, and SVM was tuned with an exponential cost function and linear gamma function, and that'll be much more clear in a second. And then finally, evaluation and comparing the models. The evaluation that was performed basically just evaluated 3 different instances in the validation set and see how each model performed, and then calculated the MAD and MSE of each of the models to see which model had the best fit. So now I wanted to talk about the last 3 stages of the CRISP-DM pipeline, but in the R notebook, so it's much more concrete. So here we're going to be talking about the data exploration, the modeling, and the model evaluation. So let's get started. So in this notebook, the first thing that basically happens is data is queried in and displayed down here, and then we basically just jump right into the data exploration. And one of the first things that I do is normalize the data. It's pretty standard. Just take the z-score so that I can not only calculate outliers but also have the data normalized. So there it is. But where it really gets interesting is with the outliers. So an outlier is considered to be anything greater than 3 or less than 3 standard deviations away from the mean, less than negative 3 standard deviations away from the mean. And so kind of what that looks like is after I calculate those, I find that quite a lot of rows have outliers in them, and these would be each one of the rows that have at least one attribute as an outlier, and that turns into quite a lot of zip codes that also have outliers in them. So this kind of surprised me, and I wasn't entirely sure if this is kind of as a result of the distribution of the data or some other factor that really needs to be taken care of. So before deciding to remove any of these outliers, I performed a little bit more data exploration, specifically with data plots, to see what was really going on here. So in the data exploration phase, mostly just scatter plots and histograms were created, but I'm going to show you the 3 most important ones here. So the first here is a median home value histogram. So this one here, and this is kind of what answered a lot of questions for me, it's really right skewed. And right around here, I see that, I feel that a lot of those outliers that we saw above are a result of being included in right there. So, and in my mind, that just kind of has to do with the natural skewness of the home values in Chicago, where a lot of them are really, a lot of homes are highly priced in downtown Chicago, which would probably be over here, with lower priced homes around here, which are kind of the suburbs of Chicago. So for that case, I didn't really want to remove that many outliers because this is just the general distribution of the home values, until I saw this chart. So this is the chart that I'm talking about. And this chart plots the time travel to work versus the median home value. And here you see with all the red data that the data is pretty normal. It's got a pretty normal spread there, minus the fact that there's a group of 6 data points here and 6 data points here. And I find out that these are zip codes 60603 and 60602. Doing a little bit more digging, these zip codes are part of downtown Chicago, and it kind of occurs to me that, oh, these probably are outliers, and I would assume that they are included right here. So when I look up at the top, I notice that 60603 and 60602 are included. So out of all the zip codes, those are the 2 zip codes that I decide to remove. So after removing those 2 zip codes, plotting the last histogram with those removed, I find that the histogram is much more normally distributed, a little bit less right skewed, and I think that's kind of appropriate. So we can move on. Finally, I move on to collinearity analysis here, which is where I remove all the values that are greater than 80% correlated with each other, all the attributes. And here you can see right around here there's a couple, and right around here there's a couple. Specifically, median rooms is negative 92% correlation with 1 bedrooms. So things like those will get removed. And after removing them, the chart looks much better and not as many high correlations exist. And then just to make sure that not a lot of collinearity still exists, PCA is performed. Here you can see that with each principal component, the cumulative amount of variance in the data set is increasing, and I decide that right around principal component number 13 is where I'm going to cut it off, because when you get to 14, 15, 16, 17, and so on, it starts to really flatten off by the amount of variance that they're increasing. And this can be shown much more clearly in the lift chart right here, where right about here is where I cut off, because this is where it really starts to flatten off. So what that looks like is all the principal components here, and next the models. Okay, so for the models, one of the things that had to be done was split training to validation. So training was 75% of the total data, and validation was 25%. And this is kind of what it looks like. So you have the training, and then here's the validation set, and then we get straight into the regression model. So for the regression model, a backward elimination is used. So the first regression model is home value against everything. That's what that dot means, and I'm going to run that right now so she can show you how that backward elimination works. And we see that 1, 2, and 3 variables are not statistically significant, PC13 being the highest, so that one's removed here. Run this. Same process is repeated. PC4, PC9, PC4 needs to be removed. And then finally, PC9 needs to be removed. And then this gets us our optimal model. So the optimal model has an R-squared of 86.5%, which is decent. It's not too bad. Using that optimal model, some predictions are made, and we notice that it gives us these fit and the lower and upper bounds. But the lower and upper bounds are quite large, which is probably a result of the R-squared only being 85. But just to make sure that we know exactly what's going on with the regression model, I calculate the MAD, which comes out to be 34,000, which is quite high. And you'll see how much higher that is relative to KNN and SVM in a minute. So the KNN model is tuned a little differently. As I mentioned in the PowerPoint slide, it is tuned using a K from 1 through 10. So we run that, and the for loop will run that. And then let's make sure this is updated. So run that. And then we see that these are all the different MADs that are calculated with each one of the Ks. And from here, we see that a K of 2 is the smallest, with a MAD of only 13,000, which is a lot less than the regression MAD. And when we run this chunk of code here, we validate that here with K of 2 is the smallest one, the most optimal. And then so finally, down at the bottom here, SVM is run. Now this takes a little minute to run to tune this model, so I'm not going to run it now, but I will show you what all the models, MAD and MSEs, look like at the end. So the comparison of models. So in this section, the MADs and the MSEs of each one of the models are combined with each other. And let's run this and then display what that looks like. So then we get a data frame that includes all of them. So as we showed before, we have the multiple linear regression, KNN, and SVM with the MAD and MSE of each one. And right off the bat, we can basically eliminate MLR just because of the fact that its MAD is so high and its MSE is so high relative to the other two. And then looking at KNN, we saw that it had a MAD of 13,000 and a lot smaller MSE than multiple linear regression. But SVM kind of takes the cake here, where it's got a MAD of 12,000, which is less than KNN's, and a much smaller MSE. And this basically means that SVM is, on average, a lot less wrong than KNN and MLR, but also when it is wrong, it is not wrong by as much as KNN and MLR. So that's basically my project and the results, and I hope you enjoy.